usually the step that I forget is to click that button. There we go. Well, I hope you guys all had a restful weekend, despite having a few exercises to do for this class. But there was nothing due, and that was the extra lecture that I delivered as a video recording. But that was only about an hour long because I figured we actually spent a lot of time, kind of interacting, answering questions, having you guys to kind of ask questions and, try to clarify points. So that's why the recorded lecture is a little bit is a little less than I think it's about an hour. So we'll see. And I'm not going to take a poll, but I hope everybody has watched that video because otherwise what we're going to do today and also the assignment that's going to be assigned today, that's already assigned today I should say, is not going to be a whole lot of, it's not going to make a whole lot of sense. All right. No questions, no traffic on the text channel so far. And for those of you who watched the video, you can probably tell me, one way or another. You can share with the whole class, or you can just direct message me whether it makes a difference or not, whether the class is interactive or whether it is just completely recorded. It feels a little strange for me to just talk to the screen and have it recorded. I would much rather have it kind of more interactive. Yeah, I think I like the interaction. But some people may not need it. Some people may not need it, and some people may not even like it. I don't want you to keep asking me questions. Okay, maybe not. All right. So we got more people in. Not quite the entire class yet, but we're getting more people in. And there are about 40 seconds left. And if you go to the off-topic channel, I found 2 articles on the internet as I was looking for stuff. I'm always looking for stuff. One talks about teaching how you think is just as important as teaching anything else. That's the first one in the off-topic channel. And then the other one compares 2 methods of instruction. Now, I have never, ever thought about how I teach my classes, which is probably a bad thing, because I probably should be paying attention to the way that I teach. But so as a result, I really do not know, adjectives that describe teaching, such as the word that I learned today, which is what is it? Didactic. Didactic. Yeah, I think that's the word. So anyway, so you can go ahead and read those articles when you have time. But right now, we are going to focus on today's topic. Yeah, so we are gradually to add on to Elijah's point. Yes, we are trying to encourage people to get back on campus, and I'm going to be one of those people because I miss riding my bike to school. And I mean bicycle, not motorcycle. I do not have a motorcycle. So I miss riding my bicycle to school. And I remember before the pandemic, I was riding my bike through the storm. It was a kind of, I cannot remember how bad the storm was, but it was raining and it was kind of windy. And I had my cape on and I stayed dry. And the only thing that I had to watch out for was the gust, because that could blow me into a ditch as I rode my bike home. So that was, yeah, I mean, it was fun. At 10 p.m., I mean, that's not a whole lot of traffic on the road. And I had all my blinking lights and stuff like that. So I kind of felt pretty safe, except for that wind. All right, so I am going to get started here. All right, so what we're going to do today is to put everything together. Okay, there are several things that we have already introduced individually, and today is going to be the class where everything is put together. A few announcements, in case you have not noticed, but it's pretty hard to not to notice, is that I have released the keys or the answers to exam 1 pi. I'm going to do it to exam 1 as well, the original exam 1. So I'm going to do that too, except I have to kind of reapply the changes to one of the earlier scripts and then rerun that script to generate the answers. So this way, you know, even though I'm kind of slow in terms of grading, that is my fault. You can at least compare the key to your answer, because I also made your answer viewable to you, so you can compare the key to your own answer. Let's see. The answers to the exercise of conversion to CNF is in the questions channel. So you can head on to the question channel if you have not checked it out over the weekend. And there was some good discussions. You know, I shared my answers and answered a few questions, and so I think that was good. And then CNF assignment is now officially assigned. Note that the expression has changed. So for those of you, I think there were 3 people who turned in their answers well ahead of time. So you guys will have to redo it. You can reattempt as many times as you want, so there's no penalty for restarting the assignment. So that should be good. Well, I mean, it's not going to be graded based on the questions from last week. I'm not sure what you're referring to. Your last week's CNF assignment, I thought I was pretty clear in class that it has not been assigned, even though I forgot to change the date. So the current one is the one that is on Canvas right now. So that's the one that I'm going to be using for grading purposes. So people who did the one before, unfortunately, all that work is not going to be graded, but the good thing is you can use it as a practice session. So the new one, you know, would not be as challenging, because, you know, it's basically just doing about the same thing. You know, it's not exactly the same, but it's, you know, has all the same elements as the other one. All right, so there's that. And what we're going to do today is to put all of these 3 things together. So we got resolution, which is proven. It has its own proof that, you know, the implication is always true. And then we have CNF. We talked about, you know, how all expressions, all Boolean expressions can convert to CNF, which is conjunctive normal form. And we also talked about proof by contradiction as a proof technique. It's a really nifty proof technique, by the way. There are a lot of theorems that would be extremely difficult to prove using a direct proof, but then if you use proof by contradiction, it's like snap, you're done. So it's a very useful technique of proof to prove something, along with in proof by induction. Okay, we are going to get into proof by induction in the next module when we talk about, I think it's the binomial theorem that makes use of proof by induction. So that's going to be another technique of proving theorems that is also very, very useful in computer science. Not so much in general math. Okay, you know, so if you're talking about calculus or linear algebra, it may not be as, you know, useful. It may be some use, you know, maybe a little bit useful, but in computer science, you know, proof by induction is extremely useful, mostly because it aligns with recursion. And recursion, as awkward as it may seem, is a very, very useful way of looking at things. So even if you eventually want to use a loop or some other iterative method to implement an algorithm, looking at an algorithm in a recursive way is very useful from the perspective of analyzing the algorithm itself. So we might get into a little bit of that in this class, depending on how much time we have left in the semester. All right, so to summarize, okay, so let's go ahead and use a few symbols. So when I use, psi, phi, and rho, over here, they are not, in the context of, whatever we have in alpha. Okay, so I'm just randomly choosing 3 Greek symbols. So I might as well just chosen alpha, beta, gamma. Okay, so it doesn't really matter which 3 Greek letters I choose here. So psi is a CNF representing I, or iota. So iota, remember, is a set of well-formed formulae that are given to you, axiomatically speaking, as statements that are always true, or conditions that are always true. So psi is basically just a conjunction of all of the elements of iota. In other words, we are just explicitly saying, okay, these things are known to be true, and here's a conjunction of all of them. Okay, not really significant other than the perspective of, oh, okay, we're converting that into a CNF, an explicit CNF with conjunctions connecting all the DEs, all the disjunction elements. And then we introduce a symbol called phi, and phi is representing a proposed theorem. So for those of you who remembered the previous lecture, phi is basically representing the theorem that I was questioning my advisor about. Okay, I was asking my advisor, "Are you really sure this is a theorem? Are you really sure that this is, a consequence of all the other assumptions that we make about the problem that we're trying to solve?" And rho is the negation, is the CNF of the negation of phi. In other words, we are negating the proposed theorem. Now, the reason why we have this rho here as one CNF is because we want to connect the two CNFs together. We want to connect psi and rho. They're both CNFs. So when you connect two CNFs using a conjunction, you just get a, guess what? Longer CNF, okay? Because on one hand you have one CNF, on the other hand you have another CNF. When you and the two CNFs together, you just have a longer CNF, and that is why we want rho to be represented as a CNF. But before it's converted into CNF, it was the negation of the theorem that we are trying to prove, because we are trying to utilize proof by contradiction. So according to proof by contradiction, if you have a conjunction of everything that is axiomatically true and the theorem that you want to prove, or the negation of the theorem that you want to prove, the conjunction should get to false. Okay, so that's the idea of this entire technique. Okay, is to utilize resolution as a very mechanical way of looking at components of a CNF, and then we will produce new DEs, will produce new disjunctive elements. But every time we produce something that's new, it has one fewer element compared to the two contributing DEs. So this way, hopefully, we'll either get to a dead end where we go like, okay, this is all we can do. There's nothing we can do with this CNF, and yet we do not have a false. Okay, or we get to a point where we annihilate these variables, inside the DEs to the point where there's a DE that has quote unquote nothing in it. Okay, so we'll get to see what I mean by nothing in it, but well, it's never really nothing. It just has the identity of disjunction, which we know as false or zero. So that's the outline of what we'll be talking about today. If we do have time left after talking about all of this stuff here, we will go into the next module that talks about probability and counting. And you guys might be thinking, but I know how to count already. What do you mean by counting? So, by means of counting, I mean how many unique lotto tickets do we get, assuming there are so many numbers that we choose out of a basket, and there's an additional what is it called? Powerball, that's it. So there's a Powerball number in addition to the 5 numbers that we choose out of a certain pool of numbers. So we might be able to get to that, we may not. So we'll go ahead and see how long it's going to take to get all of these topics out of the way. Alright, so Danny said in a makeup lecture video you gave a practice problem. Is the answer to that given somewhere in Discord? I'm not sure. I think it is in the questions channel already. It's already answered in the questions channel. Yep, there we go. Thank you, Chandra. So that was a kind of neat. That was a pretty good discussion, on both the one in the module itself and also the one that I gave in the recorded lecture. Yep. All right. Thank you, Chandra. Cool. All right, so we're gonna move ahead and start to talk about the last few things about propositional logic. All right, so we are gonna move on. So proof by contradiction is something that we introduced last Wednesday, and we pretty much are done with how it works. Okay, why does it work? It has to do with the corollary, which is this one here. And then based on that, we just kind of say, well, if we have phi as an actual theorem, if it is actually if it's actually implied by psi, then we should be able to do something like this. Okay, so we just form a conjunction on the left hand side of the implication and form a conjunction on the right hand side of the implication, except the component that we are ANDing with, psi on one side and psi on one side and then phi on the other side, is the negation of phi. So on one side we just have the conjunction between psi and not phi, and then on the other hand we have, guess what, false, because phi and not phi is always going to be false. So this is the basis of proof by contradiction, which basically states, if phi is indeed implied by psi, then we should be able to derive the constant of false when we look at the conjunction of psi, which is the collection or the conjunction of everything that is known to be true, and the negate theorem. So that is the basis. Now we're going to move on and talk about the overall strategy, which I just described. So I'm going to skip this portion here and we'll go straight to a few examples. So the first, both examples involve the same psi. So the psi in this case is not P, or the negation of R implies Q, and P or T. So that one is already solved up here. So for anyone who wants to know how we solve that one or how we convert it into a CNF, this is the expression that we saw a little bit earlier, down there. And this is the CNF of that thing. And this is one way to do the derivation. I kind of explained this one also, and I also explained how I did not follow my own recommendation of simplifying along the way, because that's how we got a little bit out of hand and got a little long. So that part is done. Okay, we want everything that is known to be true to be expressed as a CNF. So the next thing we want to do is to ask, okay, so what is the theorem or what is the proposed theorem? So in this case, in this very specific case, we have phi as not T implies P. So I just chose something out of thin air, okay, and say, okay, is this a theorem? Okay, is this implied by psi as an expression over here? Now psi is both this expression as well as this expression. In other words, if you plug both into a truth table, the column of these two expressions would be identical. It just looks a little bit different, but it really is the same thing. So this is our phi, which I claim and say, well, it might be a theorem, but it may not be, okay, but we want to prove whether it is or it is not. So the first thing we need to do is to look at the logical negation of phi, and that has to do with the proof by contradiction technique. We have to look at the negation of the theorem that we are trying to prove. So we put a negation over the entire phi. So it has not, and then not T implies P, and then we use the definition of implication so that we end up with not T or P, and then we apply De Morgan's law. De Morgan's law is negating. It works when you have a negation of a or a negation of and. So in this case, we have a negation of or. So we end up with changing the OR into an AND, and then we distribute, quote unquote, distribute the negation to each component of the original OR. So now we have not T, or and not P, and we do some simplification here, and it becomes just simply not T and not P. All right, so do we have any questions about up to this part here, up to where my mouse cursor is, like right here? No questions? All right. So for those of you who are in the design hub, you know how Randy likes to just keep clicking that key with that kind of radar effect. Mine is a little bit different. It's probably more annoying than Randy's, but this is the only one that I could find, and I'm too lazy to modify it. All right. Would it be a bad idea to convert phi into a CNF and then negate it? Well, if you did that, it's not going to be. I mean, you can still convert it, right? So you can always do that, but you might be wasting some time. And the reason I said that is because if you convert phi without the negation to a CNF first and then negate that, you end up with, you can end up using De Morgan's law, but then you end up with a DNF. You end up with a disjunctive normal form, and that's not what we are looking for. So that's why I personally would do the negation first and then convert to CNF. I mean, after you have a DNF, you can still convert a DNF into a CNF. A DNF is a disjunctive normal form. You can always convert into a CNF. Both of those have equal expressive power when it comes to being able to express every possible Boolean expression under the sun. It's just that it's one extra step that you normally do not need to go. Now, the conversion from DNF to CNF is really mechanical. So it's not like it's not gonna take a lot of time. It is mechanical, but it's still an extra step, an extra chore that you probably do not need to do. So I hope that clarifies Luke's point. So it's not a bad idea per se. It is just it doesn't gain you anything. It's not wrong. It just doesn't give you a whole lot of advantage over the way I do it here. All right, cool. All right, so now we move on and we look at the negation of phi as a CNF, and then we look at psi also as a CNF. And then what we do is we just AND those two together. So when we AND those two together, we end up with, I call this a super CNF. It's definitely not a technical term, okay? It is, I just call it a super CNF. But what it is a CNF that combines everything that is known to be true, all the axiomatic truth is captured, and it also captures the CNF that represents the negated theorem that you want to prove. So even though I just call it CNF, super CNF, it does have a specific meaning, for this kind of casual term here. All right, so we move on, and then we try to do resolution here. So in order to perform resolution, which is something that we talked about more than a week ago, so unless you review your material, you jot down the notes, and then you absorb the content, you might have forgotten what resolution needs. So what resolution needs is some term in one disjunction and some other term in another disjunction, and those two terms must be complements of each other. And that means one is going to have a variable, and then the other one would be the negation of the very same variable. So in this case, I do this kind of in a more systematic way, and you guys can do in whatever way you want, okay? But I try to do it in a systematic way, so this way I don't miss anything. So the way I do it is I start with the first disjunction, and then I would try to match the first disjunction to every other disjunction that is after it. So I try to match not P or R with not P or not Q. And I'm looking for what again? I'm looking for a variable that is non-negated on one side and negated on the other side. So I cannot find a match, right? Because not P super CNF. That is quick. Did you just make it, Danny? Oh, that is cool. So now I need to think of what would be equivalent to the with what would be equivalent to kryptonite in this case. All right. So we can see these two disjunctions cannot match, okay, because they both have negation of P, okay, so that's not a match. One has a non-negative version of R, but the other one does not mention R at all. The other one has not Q, but we don't find Q in the first one, so they cannot match. So if we try to match the first disjunction with the third one, once again, there's no match because I mean, they don't even share a variable, okay? So if they don't share a single variable, there's nothing is going to work. And then we try to match the first one with the last one, and it's not going to work because, they both only have the negation of P, and that's not going to work. And then I move on to the second one, and I try to match the second one with the third one and then the fourth one. So you can see how this is not going to work. And between the second one and the fourth one, that's not going to work either. Then I start with the third one, or the second to the last one, and they do not work either. Okay, one is a negation of T, the other one is the negation of P. Once again, they do not even share a variable, so that is also not going to work. Alright, so Danny asked, so you're trying to match this pattern to the patterns in resolution. Yes, that's exactly what I'm trying to do. So I'm trying to see if I can apply the transformation that we specified in resolution. We're trying to find out whether two of these things can match the two templates on the left hand side of the transformation rule. If we can do that, then we can find that rule and end up with a new expression, which will be then added to the conjunction. Unfortunately, it doesn't work here, right? So we come to the conclusion that this is a dead end. Okay, it is a dead end, which means we cannot get to false. We cannot get to 0. So whenever you cannot get to 0, you have to make a conclusion and basically say the proposed theorem, in this case phi, is not a theorem. Okay, but that's the only thing we can say. Okay, we can only say that phi, which is not T implies P, is not a theorem. It is not false. Okay, it can very much be true, but it is not implied by psi. That is the only conclusion you can draw, is it is not implied by psi, and hence it is not a theorem. Alright, so I'm going to pause here and see if you guys have any questions. I know Danny is typing, and so is she. If I mispronounce your name, you can please go ahead and correct me. I do not speak Cantonese, so I mean I speak Cantonese, but I don't speak Mandarin. So all the curl tongue consonants, they are all about the same to me. I'm sorry, I just don't do curl tongue stuff. Sorry. Alright, so the question from Danny is saying, if you had something like not R added to the conjunction, then we can resolve with not P or R. But then we will end up with a product, or the output or the outcome of the resolution is just going to be not P itself, which we already have. So even if with not R as another component to this CNF, we would still be hitting a dead end, even though we could carry on one step of resolution, but because it ends up with the same thing that we already have here, it would still be a dead end. Oh, the next example is going to show what happens when you have a single item. So that's when we get to the next proposed theorem, that question will be addressed. Yep, there we go. And then we got Luke and Chris typing, so we're gonna wait a little bit. So this is why the recorded lecture is shorter, because we spent quite a bit of time to do the interaction and clarification, which I think is really important. All right, so Luke typed, so phi doesn't necessarily follow from psi, but phi could still be true given PHS, psi. Right, because the variables are variables, right? So, in other words, when we look at psi here, psi doesn't say a single thing about whether P has to be true, R has to be true, or Q has to be true. Psi here really is just saying, okay, this conjunction has to be true. So how do we make this conjunction true? Well, let's take a look, right? So in order to make this conjunction true, we got quite a few ways to do it. We can make P false, right? If P is false, then the conjunction is guaranteed to be true, because in that case, not P or R is going to be true, not P or not Q is also going to be true. So having P by itself to be true is going to make psi true. If we make R and not and if we make R true but Q false, that would also make this conjunction true, because in this case R is part of the disjunction here, and then not Q is part of the disjunction here. So if R is true, this disjunction is going to be true. If Q is false, then not Q is going to be true, which makes this disjunction true. Then we have true and true, which makes psi true. But then phi is not following that, right? Phi is not necessarily going to be true, because the easiest way you can make a case where psi is true but phi is false is easy. The easiest way you can make this happen is to make P false. That will automatically make psi true. But then you make T itself, let's see, false. So if T is false, then not T implies false, or I should say, true implies false, is going to be false. So the implication is going to be false, which means there is a way, at least one way, to make psi true, but phi false, which means psi implies phi is not happening, right? All right, and then Chris says, contradiction can prove something true, but can't prove something false. It depends on whether you are using the word contradiction in the context of proof by contradiction, which is actually trying to prove a theorem being a theorem, or whether you're trying to use the word contradiction in the sense of proof by not proof by contradiction. This is it's more like disproof by contradiction. It's there's a term to that thing. There's a term to that technique. To prove a theorem is wrong, you just need to find one example to make it false. Oh, okay, thank you for the clarification. Proof by contradiction can prove something true, but it can't prove something is false. Technically, that is not the case either. Proof by contradiction, like any proof, is only going to prove an implication. It's only going to make a connection between what is known to be true, all the axiomatic truths, and the expression that you say, okay, what about this one here? All you're doing is to form a long or short chain of implications. So it's all about just whether what is given to be true is implying the theorem or not. If it's not implying the theorem, then the theorem is not a theorem. It's just an expression, but it is not a consequence, a logical consequence of what is given to you to be true. So we kind of have to step away from true or false, because what you're trying to prove is whether the implication itself holds or not. I'm not sure whether that is working or not. I can give you another example of proof by contradiction after we finish with the second example of resolution. So let me know whether that's going to work with you guys or not. And I'm going to set up the row-taking activity so that you guys can get it out of the way. But meanwhile, if you guys have any questions, please do not hesitate to ask. All right, so we got the row-taking activity here. I will first show you the answer. Some of you probably would have guessed the answer already. Psi implies phi. Yeah, so that's all we are trying to prove, is whether there's an implication or not. So the word of row taking was a word that I mentioned earlier in class. It is didactic. Didactic. There we go. Alright, so let me go to release it. It's not released yet, so if you refresh, it's still not going to show up. So let me go ahead and release it and give you guys 45 p.m. So we have a little less than 15 minutes, but that's still plenty of time. Or what I would consider plenty of time. And of course, somebody's going to say, but this, the fact that you're taking role is proof that you are teaching in a didactic way, because that's what elementary teachers do, right? They take role. So this is an example. Proof. It's not proof by contradiction. I cannot remember the term for that. There's a term that says if you can counter example. That's it. Okay. So the fact that I'm taking role is counter example that I am not teaching in a didactic way. Yeah. I got to apply logic in this class, right? I mean, this class is kind of about logic. At least a good portion of it is about logic. So there we go. I'm not seeing any feedback of anyone not being able to get into the quiz, so I'm going to assume everybody's in and gotten it done already. All right, so we're going to move on. Okay, so what we're going to do is we are moving on to Phi Prime. Okay, so this is Phi Prime, which is not the derivative of phi, because we are not, remember, we are not doing calculus here. So the prime is really here just to differentiate this proposed theorem from the one that we mentioned earlier. That's it. Okay, so this one says P implies not Q. Okay, so this is a proposed theorem. I want to know, okay, whether psi, which is the same as the same psi up here, so I want to know whether psi in either form is going to imply P implies not Q. Okay, that's what I want to determine. So I could have gone about doing this using the Boolean algebra way, which is going to be just an exercise of Boolean algebra. But since we are talking about a mechanical system, so now we are trying to do this using using CNF, resolution, and proof by contradiction. So the first thing we need to do is to negate the proposed theorem. So phi prime is P implies not Q, so we now have to negate the entire implication. And then we first convert the implication to a OR with a negation of the left-hand side of the original implication. That's based on the definition of implication. And then we apply De Morgan's law because we have a negation of a OR that converts the OR to an and also in the same process we add a negation to each of the term in the original disjunction. So we end up with a not P and not Q. Do a little bit of simplification, double negation goes away, and now we have P and Q, which by itself is CNF. So are we good here? Are there any questions about how the negation of phi prime is converted into a CNF of P and Q? All right, so we are good here. I mean, if there are any questions, we should address those questions before we move on to the actual resolution step. All right, no questions. Okay, no questions that I can see. All right, so now we combine the two conjunctions and we make a quote-unquote super CNF. And this is my mistake. I forgot to put a backslash in front of phi, so it's supposed to read as not phi, the Greek letter prime. But it's still understandable what it is. It's just kind of spelled out instead of being a Greek letter. All right, so we combine the psi portion with the other. Oh, okay, so we got a question. Okay, so it is probably a good idea not to use the general text channel during class, because I can't look at both the general text channel and the channel of today's date at the same time. So if somebody is posting a question in the general channel, I have to click on the other one and then go back to the original one, to the one of today. All right, so that one is about. Okay, so the resolution one should not. So don't pay attention to the resolution one. It is not assigned. Okay, I've never assigned the resolution assignment. I just released the CNF assignment today. Let me see if I can do this. I don't think I can do it if somebody has touched it already, but I will give it a try so this way we don't get too confused. Alright, so the resolution improved by contradiction. Let me see if I can unpublish it. May not be doable. Oh, it is doable. Okay, so there won't be any questions from now on because it is not assigned. That is not an assignment. I should say, be more clear. Resolution improved by contradiction is not an assignment. We do have an assignment of CNF right now that is due next Monday at noon. Alright, cool. And I'm gonna do this. As I navigate back to today's text channel. There we go. Alright. Chris said, not P and H and I. And then a prime. That is correct. Chris is correct. It is not that. Alright, so let's see how resolution works, okay? So the first line is representing just a concatenation of the two CNFs. So we got, the first three terms are the same as before. Nope, I take it back. The first two terms are the same as before, and then we have the other two terms which are coming from the negation of Phi Prime. So I'm going to apply the same technique as before. Okay, take the first disjunction and try to match it with the second, the third, and the fourth, and see if we can apply resolution in any one of those steps. And you will find that we can indeed apply it. Okay, so I'm not actually following my own instruction here. When I solved this, I was trying to do it as quickly as possible. So the way I did it was to look at the second term and say, oh, look at these two. Okay, look at not P or not Q, and then look at P itself as a disjunction term. And we say, well, can we find a variable on one side and the negation of the very same variable on the other side? So the underline here is really just to highlight here which two terms are being used to make a resolution work. So in this case, we have not P on one side, we have P on the other side. So now we say, oh, resolution works. So in this case, when resolution works, the end result is just not Q itself, which we add to the very end of the original CNF. All right. So that's one step. This is applying resolution once. So let me just pause here and make sure everybody knows what is going on. Why I can decide that the second and the third disjunction items do have a match, and after the match is done, I fire the quote-unquote rule, and the result is not Q, and I just append it to the end of the conjunction to the CNF. So let me just kind of pause here and make sure that there are no questions before I proceed to the next step, because the next step basically is checkmate. It's done. Yep, that is the resolution rule. So Danny is correct about the resolution rule. All right. It means that we are just using the patterns matched in order to create a new well-formed formulae. Well, not so much to create. I should kind of refrain from using that word. We are actually just labeling another well-formed formula as derivable, so that it goes all the way back to whether something is derivable or not. All right, so Elijah is asking, so which are you using for phi, psi, and rho? All right, well, that's a very interesting question in a way. Okay, so psi is the one where it is negated on one side and not negated on the other side. So that's pretty clear which one is psi, right? So psi is p. If I remember correctly, phi is the one on the left-hand side, the leftover part of the left-hand side. So that's just going to be not q. Not q is our phi. Now, the interesting question is, but what about rho, right? Because p is all by itself. There's nothing else in that quote-unquote disjunction. Remember what I said? There's always a or zero in a disjunction. So that zero is basically taking the role of rho, taking the role of rho. One with a L and the other one without. Yes, so Luke is correct about that. Yep. It's implicit, and that's why it's never really explicitly represented here. Because anything or false is just the first whatever anything, so I don't bother to say, oh, this is not Q or false. Excellent. That was a good question, because we want to look at the rule and go like, okay, but what about these various parts? Well, as it turns out, the or false is implicit, so the false is in this case playing the role of rho, the letter, the Greek letter. Cool. And there are two more people typing, so I'm going to wait until those questions are asked and addressed. All right, so Nathan asked, cool, so we can execute this rule with less than 3 explicit components by using implicit components. That is correct. And then Danny is making a point. I at first thought it would be not P or not Q or P, not Q or P. We do not have a not P or Q, not Q or P, because P is P or P. Not really sure what Danny is referring to about the not Q or P, because we don't have any term like that here. Yeah, I can. Yep. It can, it just doesn't help, because in this case you would have annihilated the not P on the other side, but you'll be appending P to the other one, and it's just not very helpful. It's yes. Yep. So in the end you end up with P or not Q as an added term. Yes. All right. But we know that term is not going to be very helpful, because this is a conjunction, and in a conjunction, if you have a term and a more general version of that term, which means one is true, so the more specific term is true less often, or there are fewer rows in the truth table in which that expression is true, and then you have a more general term, which means there are more rows compared to the first one that are true in the truth table. The more general one is not going to be contributing anything. So even though, yes, we could have added P or not Q as an additional component to the CNF, ultimately, it's not going to be useful because that term can easily be simplified out if we are not limiting ourselves to only be using resolution. And then Luke said, I think you mentioned this earlier, but you are specifically applying only the resolution rule in these steps. Yes. So we are not using anything other than resolution in these steps. Now, the only one that I am implicitly using would be commutative rule. In other words, if the two things that we are resolving are out of position, that one is not the last one and the other one is not the first one of the two respective disjunctions, I'm just implicitly using the what do you call it again? Commutative law to say, okay, ordering does not matter. Just find one that is a rare variable, and then the other one is the negation of the same variable, and we call it good. So that's used, that's applied implicitly. All right, and then he said, and it is more useful to use the 0 here because it gives an easy answer that the entire conjunction is false. That is correct. So if you can perform a resolution, which we're going to do in the next step here, and it ends with 0, which means 0 or false is now derivable, then it is added to the conjunction. Now, if you add a false to a conjunction, in other words, if you have blah 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 and false, then the blah blah, then the entire thing is guaranteed to be false, because you only need false once in a conjunction for the entire conjunction to be false. And once you have false, you're done, because this is what we're trying to get to in proof by contradiction, is to say, okay, we want to prove that the conjunction can become false. So that is the key. That's why we are doing resolution. And then Elijah said, so I thought resolution gives a disjunction. So it does. Okay, a disjunction is the outcome of applying resolution, but the disjunctions, on the left-hand side, to match the pattern, those need to be connected in a conjunctive way. So we are using conjunction as a way to connect the disjunctions, but the resolution itself is producing additional terms, and that term is going to be the term produced by resolution is a disjunction, but we're adding that disjunction to the conjunction as we go. And the disjunction with 0 is implied. That is correct. Yep. So in other words, okay, with every single disjunction here, with every single term in the conjunction, you can just say, okay, not P or R or false, right? Not P or not Q or false. P or false. Q or false. Not Q or false. So the or false is always there. It is just implicit because I don't feel like typing a whole bunch of / VEE 0 in every single one of these expressions, because it's always there. And there are a few more people typing, so I'm gonna continue to pause. Yeah, but then it goes to and false at some point. So we are not quite there yet. Okay, we are still on the second line of the steps of applying resolution. Yep, Chris is correct. So false is basically, you can call it the identity with respect to disjunction, and then true is the identity of conjunction. Kind of like plus 0 in arithmetic and also times 1 in arithmetic. It doesn't really change the value of whatever you are adding 0 to or whatever you're multiplying 1 to. They're called the identities with respect to the operators. And I think Chris is ready to take abstract algebra. Abstract algebra, I think, is a good class for all computer science people to take, by the way. Yep, we get that in the second step, which we are going to do. I just want to pause on the second line first before we move on to the third line, because the first line already indicates what resolution is doing. All right, so Elijah says, okay, for negation of Q on line 2, negation of Q on line 2. We need the last item. This is the product, this is the outcome of applying resolution. Do we go from disjunction to conjunction? No, this is a disjunction by itself, which is the product of performing resolution using matching the two patterns on the left hand side of the rule. So not P or not Q is one component, and then P or false, okay, is the other one. So when we use those two as the left hand side to match the left hand side of the resolution rule, we end up using P as our psi, we end up using not Q as our phi, and then we end up using false as our rho. So once we fire the rule, we end up with a well-formed formula that is now marked as derivable. So that formula, or that expression, is technically not Q or false, because there's a or false implied by just the P itself. But since I don't bother to write or false, it is simplified when I write it out here as just not Q. So I'm not sure whether that addressed Elijah's question or not. And then linear algebra, okay. And then Luke said, yep. Okay, yeah. All right. So I think we are good. And Chris summarized, the resolution, or how the resolution rule as a transformation, is applied in this case. Yes, so the product or the outcome is added to the list, because remember what this conjunction is. The conjunction is basically representing everything that is known to be true. So we start off with what is known to be true, which is from iota. We have to add the negation of phi prime in this case, because that's something that we want to prove. But everything that we derive, okay, is implied. So as long as you're adding something that is already implied by the other components of the conjunction itself, it doesn't change the meaning of the conjunction by adding components that are implied by the rest of the conjunction. Okay, let me clarify that point, okay, because I know how confusing it sounds, so I'm going to clarify that point. Okay, so what I'm trying to illustrate here is, if you have a conjunction and one component of the conjunction is already implied by the other conjunction. So one way to represent it is to say, let's see. So I will refrain from using PQRST and the Greek letters that we have been using. So let's just use A, B, and C. Okay, so we have A implies B as one thing, and then we say A. Okay. So I'm gonna close it so that you guys can see what I mean by that. Okay. So now we have a conjunction where we have A implies B is one of the components of the conjunction, and then we have A as a conjunction. So now the question is, how does this compare to the same thing, which is A implies B and A, which is what we started off with, and now we say, oh, let's add B to it, because if I know A is already true and A implies B is true, then B is also going to be true. So now we look at these two expressions and we ask, are they exactly the same? That's basically what the question is. Because if this is true, okay, if this equality, let me point out which equality here. So if this equality holds, okay, regardless of what A and B are, then we can use the result of resolution, okay, the right hand side of the resolution, and we can add it to the conjunction without changing the quote-unquote meaning of the conjunction. Now when I say the meaning of the conjunction, I really mean in the truth table, which rows are zeros and which rows are ones. Okay, so the question is, how do we prove this? Oh, okay. Symbolic logic is definitely related to what we are talking about here, but it is not a prerequisite of this class. I guess we can make it a prerequisite to this class, and I think more people will be complaining. It's like, but I know all this stuff already. I should be able to take this class. All right. So getting back to this point here. So tech is claiming this, right? So you look at this and go like, okay, if tech says so, it's good. Is that what is that what you're gonna do? Maybe. I mean, I really have no idea what you guys are gonna do, but I'm gonna say, hold on a second here. How do we know that? How do we know this equality holds? How do we prove this, right? And this one is very easy to prove, okay? Because we only have two variables, right? And both sides are Boolean expressions, and I want to see if the two Boolean expressions are equivalent. So how do we do this? It's a technique that we have used quite a few times already. I have probably even given you ungraded assignments like, okay, you guys go do this, but I'm not going to use class time to do it. Truth table, yes. You can use resolution too, okay? You can definitely use resolution. That's because implication can be rewritten as a or, right? So Luke's suggestion is actually really valid, because what we can do is to say, okay, we'll just go ahead and use the definition of implication, and instead of using implication, now we have just negation of variables and disjunctions. So when you have something like this, guess what? You can prove, well, okay, so this is now proven by using algebra to basically say the result of resolution can be added to the entire conjunction without changing the meaning of the conjunction itself. But for those of you who really do not want to work with symbolic math and whatnot, or try to avoid it as much as possible, you can use a truth table. So just go ahead and make a truth table. It's going to have 4 rows in this case, because we have 2 independent Boolean variables. So you have A being true, true, false, false, and then B being true, false, true, false. Okay, and then you evaluate the expression to the left of the equality. Okay, has a whole bunch of true and false values. You evaluate the expression to the right hand side, which also has its own true false values, and if they have the same true values on the same rows and the same false values on the same rows, then the two expressions are equivalent. Why would it resolve to 0? I do not see how this would resolve to 0, because B is hanging around by itself. Nobody's going to annihilate B. There's no negation of B anywhere within the conjunction. So B is just going to live forever. I mean, because there's no anti-B in this universe to annihilate this B. But use a truth table. Okay, I'm not just casually recommending. I am seriously recommending you to use a truth table and see for yourself that this works. Okay, because this is important. Okay, if you can prove this, okay, then we can go back to what we were talking about, and then we start to understand why the result or the outcome of resolution can be added to the original conjunction. Now, it is really important to add it to the conjunction, because whatever term you produce from resolution, that can contribute to another resolution. Okay, so it might take you a few steps, to kind of get rid of enough variables in order to end up with a false. Okay, this is a fairly simple example. Okay, it doesn't really go from like 5 variables in a conjunction, and each time you only get rid of one of them, so it will take 5 steps to get to false, right? This one is really easy. Okay, it takes 2 steps. Okay, because the next step here is just looking at this Q and then looking at the not Q that we just quote unquote produced, from resolution, and we go like, oh wow, this is going to work because this Q is really technically Q or false, right? This is technically not Q or false. So we look at those two disjunctions and ask, okay, can we find a variable where it is not negated on one side and negated on the other side? You go like, yeah, we find it. It's Q. What about phi in this case? Phi is false, okay, because it is the implicit false coming from Q or false. And what about rho? Rho is also false because it is the false that is implicit in not Q or false, right? So we end up with false or false as the outcome, which is the well-formed formula that is now marked as derivable. So I just simplified the false or false to just a single false because that's why write the false or false when it's just false. But once we add this false to the entire conjunction becomes false. I don't really care the value of these guys over here, but this false over here guarantees the entire conjunction is going to be false. So now we have a conclusion, right? The conjunction between psi, which is everything that is known to be true, and not phi prime, which is the negation of the theorem that we are trying to prove here, is ending up with a value of false. That is the conclusion that the proposed theorem phi prime is indeed implied by psi. Okay, that's it, right? I mean, we are right at the end of the entire module. This is basically the last sentence of the entire thing. And don't mind about this part here. This is just me playing around with a logo. That's one way to spell tack. It's just that the letters T and A are rotated. So it's just me having fun. Don't mind this one here. That is funny. Oh yeah, we are now done with the entire module, but you can see this is a long module because there are so many items to the very last thing that I want to say. It's like, oh, we can actually use mechanical ways to prove theorems. Now, obviously, the really difficult part here is converting any Boolean expression into a CNF to begin with, and even that part can be mechanized. Copyright logo. It's called a trademark, but I'm not trading anything. Well, trade implies that it goes in both directions, but it does go in both directions. I mean, my interaction with you guys and other professors definitely is a two-way street. I learned stuff from many of my students. So you can call me a trader, I suppose. And I think in the ideal case, a class is kind of like a trade center, not only between me and you guys, but also between you guys. I mean, this is one reason why I chose to use Discord, because in Discord it's pretty easy for you guys to kind of spin off, make your own groups, make your own servers, okay, and then just kind of have your own little study groups going. So I don't give knowledge. I just share with you what I know. There's a difference. There is a difference. It's a very minor difference, but a significant one. Sharing with you what I know has no implication that what I share is right or true. Which I think is a good assumption whenever you take a class from any professor. Is kind of make that assumption. It's like, okay, let's just say the professor keeps making mistakes left and right. How can I tell whether the professor is making a mistake or not? But that's just my take. You don't have to use that view. All right, so let me take a look at the time. We got 15 minutes left. If we have no more questions about CNF, resolution, and proof by contradiction. Oh, right, I did say that I would give you another example of proof by contradiction, so we're going to do that. Yeah, I don't even. Okay, let me try to pronounce that word, and I'm going to cheat here. So we'll. Yeah, I remember it means theory of knowledge. And my kids went to a school where they have a class called theory of knowledge. Um, and from what they told me, is actually quite interesting. You guys cannot hear it, but I just used the Google to find that word, and it pronounced it so quickly. I need to hear it a few times. Epistemology. 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 Okay, there we go. I'm not an audio person, so words are difficult for me to both to say it, to formulate words and sentences, and also to parse it. And no, it has nothing to do with my natural language versus my second language. I do equally poor on any language. So there you go. All right. So, without any additional questions, we shall move on to counting. At least get into the concepts. All right. But if you do have questions, go ahead and post it. We can always kind of go back and talk about that. All right, so we are moving on to discrete probability, but before we can talk about probability, which is the likelihood of blah blah blah, like what is the likelihood of me winning the jackpot of the Powerball lotto game? Okay, that might be something that you are interested in finding out. Okay, so that's probability. Okay, what is the likelihood? What are the chances? But before we go there, we have to talk about counting, because until you know the number of unique tickets, okay, from any lotto game, you may not be able to figure out the chances of winning the lotto game. Okay, a specific prize doesn't even have to be the prize, the jackpot, but any type of reward from buying a lotto ticket. If you want to know the chances, you need to first know how to count. So that's what we are trying to do here. Yep, that's Chinese in simplified characters. Um, the funny thing is, if people give me a lot of technical terms in Chinese, I just say, just give me the English version, because I'm not well versed in technical terms or anything other than colloquial or casual conversation. So that's the thing. All right, so let's go to counting, and there's a very specific way of introducing into the topic here, and it looks kind of boring, and there's a lot of symbols too. I'll just kind of fast forward to something that you guys would go like, what the? Yeah, this is not it yet. This is not it yet. This is bad, but I think this is worse. I think this is basically this is the pinnacle of what is this symbol doing here? You have like a big U notation here, and then the variable that we are iterating through is saying, okay, for all elements of blah blah blah, we are going to do this, except that blah 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 is the return value of recursively applying this U function to something else. So we'll get to that. Okay, yeah, trust me, we will get to that. But before we get to that, we're gonna talk about something that you guys are probably gonna go like, okay, I'm glad we are talking about something that is of some interest to me. So we're going to go to the Lotto website, and specifically we're going to look at Powerball, because last time I checked, nobody won the jackpot. So I think the jackpot is actually pretty good, at least when I checked it last time. Oh, okay, I guess somebody won it at some point in time. It's only down to 156 million. It was, I'm not sure. Huh. Okay, never mind. Never mind. And I'm not sure whether California has its own Powerball. Okay, let me check that. California. There we go. State lottery. There we go. So it's the same. Okay. So I think the jackpot was paid out, to someone. All right. So the question is, what are the chances of winning the jackpot of Powerball? Okay. So there. Oh, it's a California only game. Okay. I got mixed feelings about that statement, but I'm not going to talk about that. Anyway, so now the question is, how is this game played, right? So we want to understand the game first. So we go to how to play. This is something that's really enjoyable. Every single time I get here, it's really funny. I'm just reading that. I'm freaked out, insecure, neurotic, and emotional. I can actually think, I'm just mapping it to MBTI types as I read those words. But that's sidetracking also. Okay, so here's the game. So the game says, pick 5 numbers between 1 and 69. Now that implicitly is saying the ordering is not important, right? Because otherwise it would have said pick 5 numbers in a sequence between 1 and 69. And since it did not say the ordering is important, or there's no word here to say it is important, the ordering is not important. And one Powerball number between 1 and 26. All right, so right there, okay, right there, understanding that the jackpot means matching everything, all 6 numbers, are matching. So now we want to figure out, okay, so how many tickets are there? Okay, how many unique tickets are there? All right, so we will go to my little notepad here, and we're gonna start a new list. And we ask the number of Powerball tickets. And we only want to count the unique one because they are not guaranteed to be unique, which adds a whole new dimension to the analysis of the chances of winning. When is it worthwhile to buy a lottery ticket? So it does add a new dimension to the degrees of freedom here. All right, so the first thing is, okay, so we have 69 numbers to choose from. So the first thing we notice is, okay, pick any number as the first number, and then okay, I'm just trying to figure out which symbol I want to use for multiplication. I'm going to use C dot here. Okay, so 69 times 68 times 67 times 66, and then times C dot 65. Okay, $69. Nope, there we go. So we basically say, okay, the first number, it can be any one of the original 69 numbers, but it is without replacement, which means once you have chosen a number, you cannot choose that number again. So that's why we only have 68 choices for the second number. And once we have chosen 2 numbers out of 69, then we only have 67 left for the third number, and then 66 for the fourth, and then 65 for the fifth number. And then we say, okay, but then remember there's a Powerball. So the Powerball is 1 out of what, 29? I cannot remember. My short-term memory is really, really bad. 26. Okay, so 26 of those. So you say, okay, times 26, But this number is not right, okay? This number is not right because it is assuming that ordering is important, okay? So if you choose 1 as the first number and then you choose 2 as the second number, it would be considered different because it will be counted again compared to choosing 2 first as opposed to choosing 1 first. In other words, if you look at the sequence, okay, simple sequence of 1, 2, 3, 4, 5, it is considered different compared to 5, 4, 3, 2, 1, which is different from 5, 4, 1, 2, 3, and so on, because ordering is important. We are counting the same 5 numbers, but if the ordering are different, it is counted, again and again and again within this part of the number. Let me put parentheses around the part where that is a concern. Okay, so I put a pair of parentheses around the multiplication where, but Tech, aren't you, not just double counting and triple counting? Aren't you counting a bunch of sequences over and over again just because the ordering are different? And the answer is yes, I am doing that, which means this answer is incorrect. Okay, so now the question is, so how do we fix that? How do we fix that problem? So to fix that problem, we basically say, well, but okay, let's just consider the 5 integers of 1, 2, 3, 4, 5. Okay, just forget about the rest, just 1, 2, 3, 4, 5. So the question is, how many times can I count 1, 2, 3, 4, 5 when the ordering is changed? In other words, the question is really asking, how many ways can you order 1, 2, 3, 4, 5? It will be 5 factorial. That is correct. Because if I give you 5 numbers, okay, so just kind of imagine that I give you 5 pieces of paper, 1, 2, 3, 4, 5, and I put it in a bag, and then I say, okay, just pick the 5 pieces of paper out, but this time I want you to line them up, okay, once you pick out those 5 numbers. How many ways can you line up those 5 numbers? So now the question is, well, we kind of need to look into that. So we are going to use a fraction. Oops. Oh, I just type a key. All right, so I'm using a fraction here, and I'm asking what should go into the denominator of the fraction. And obviously, Chris already provided an answer to this. But why is it 5 factorial, right? So the answer to that question is, so if you give me a bag that only has 5 numbers, okay, and in your head you can just kind of imagine those numbers are 1, 2, 3, 4, 5 in a bag. So I ask you, okay, how many choices do you have for the first thing that you draw out of the bag? Well, since all 5 things are still in the bag, I have 5 choices for the first one. What about the second one? Since I'm not putting the first number back into the bag, there are only 4 of them for the second one. What about the third one? We got 3 left. What about the fourth one? We only got 2 left. And what about the last one? Well, Tech, is that a trick question? Because we only got 1 thing left in the bag. Obviously, there's only one way to choose the last item in this case. So this is basically the number. Okay, so if you just figure this out, this is basically the number of unique tickets when it comes to the Powerball lotto game. So the next question is, all right, so are we done with this module? I mean, looks like we are done counting here. Well, not quite, right? Yeah, I wish it was that simple. Not quite, because the first thing we want to do is to say, okay, so this is very specific to the Powerball problem that we are trying to solve here. So the next question is, if I turn those things into variables, okay, how many numbers were originally available for the part where the ordering is not important. The 26 is really inconsequential here, okay? The 26 here is not really that complicated to figure out because that's the Powerball number, which is independent to the other 5 numbers that we choose. So it's the other 5 numbers that is interesting, because now I can start to ask you questions like, so how many unique tickets are there that will match 2 of the 5 numbers that are chosen here and not matching the Powerball number? And then some people may ask, but why do you want to know that? Well, that's because those are also winning. So, game odds here, you can see, how you can win a smaller prize if you have 2 of the 5 matching and also the Powerball. Okay, so if you only have 2 of the 5 matching, you have to have the Powerball also to match to win a prize. But if you match 3 of the 5 of the numbers and not match the Powerball, you can still win something. I mean, there's still money associated with it. So Chris has Not sure what that number is, but the odds of winning the jackpot is 292 million ish. So let's call that 300 million. So if every person in the United States buy one ticket, then one of us is going to win. That's kind of the chances of winning the jackpot. If each person were to just buy one ticket, which is not limited, right? Because you can buy as many tickets as you want. So here comes the next question. Okay, so I know we are running out of time, but I want to kind of plant this idea in your head first so that you can chew on it until we talk about this again on Wednesday. So the question is, let's just say that the jackpot is $300 million, okay? And you say, and go like, if I go to the bank, okay, and ask the bank to loan me 292,201,338 so I can buy every single possible unique number for all the tickets, then the worst it can be is just I win the jackpot, I pay the bank back, and that's it, right? Well, the answer is it's not quite that simple. Okay, so there are a few things getting in the way. The first thing is called taxes. Okay, because the state government and the federal government wants its share of the income, and that usually is like one half already. And then the most unpredictable one, I mean, taxes is predictable. Okay, so if you want to factor that in, it's easy. Okay, just call the franchise tax board or something and just have them to tell you, okay, if you have an income of $300 million, this is going to be the taxes. Okay, so that part is easy to figure out. What is difficult to figure out is how many other people are going to do the same thing. That is going to be the difficult part, because you can have a lot of people buying tickets, you can have multiple people winning the jackpot, then the jackpot is going to be split among all of these people. And that is the really, really unpredictable part, because every single time there's a huge jackpot, you probably can look back into the history of Powerball, there will be multiple jackpot winners. So the bottom line is, don't buy lotto tickets. I mean, that's basically the bottom line. After I exceeded the class time by almost 4 minutes, that's kind of the conclusion we're getting to at the end of today's lecture. So I'm done with the lecture. If you guys have questions, you can post it on the text channel, and if there are not a whole lot of questions, I will kind of get out of the voice channel. You guys have a good day, and I'll see you guys on Wednesday. I think people are hurrying, to get out of the class to go buy lotto tickets. Yep, you guys too. Have a nice day, and get started with the homework, because it might take you some time to get it done. Well, a surefire way to win the jackpot ticket does not mean it's financially advantageous. So there's winning, and then there is profitable. Those two are not necessarily the same. One does not imply the other, I should say. Yep. You can model it. Okay, so for Luke, for those of you who are still online right now, you can sort of model it, because it does have past winning numbers. And with each one, oh, this is not clickable. Let me see, where is it? Last draw. There's a historical thing that you can do. I just cannot remember how to get to it. There's some place. Oh, right. Okay, never mind. Each one is clickable. You can just click on the plus here. So you can figure out, given a particular price amount, and based on the distribution, you can go back in time and actually figure out how many tickets were sold based on a very specific price amount. So if you plot it, and just have enough historical data, you can probably predict in the future, with inflation adjusted and all the other good stuff. So you can probably predict, for a very specific range of price amount, how many tickets would be sold as a total. So you can model, the how tickets are sold, as a function of the prize money. So once that is modeled, then you can truly, have a informed decision whether to buy a ticket or not, because you can even factor in, the chances of multiple people winning the jackpot when the prize money is way, way, way up there. So there's that. Okay, because all the historical data is already here, in the it's stored on the website, so it's going to be, handy in that way. Yeah. So the amount was reset, recently, because I remember, the billboard along the highway, was advertising like 300 plus million at one point of time or another, but I cannot remember when the jackpot was paid off because I never pay attention to these things. Anyway, that's the end of today's lecture. Well, thank you for being here, and I'll see you guys on Wednesday. Bye.